Thank you very much, Kostya, for the introduction and the invitation. It's a great pleasure to be here. Let me share the PDF file I have prepared for the talk. Okay, I hope everybody sees the PDF file. Okay, so I'm going to talk about the Jordan property for homeomorphism groups mainly. And let me begin by recalling the definition of Jordan group. We can begin with a definition that depends on a number. Let's say C is a number. Then we say that a group D is C Jordan if each finite subgroup, say G of the group D, has a normal abelian subgroup A whose index in G is at most C. And then we say that the group D is Jordan if it is C Jordan for some number C. Now the most basic example of Jordan group, there are trivial examples like finite groups, and the notion is non-trivial only possibly with infinite groups. And the most basic example are the general linear groups, and they were proved by Jordan to be Jordan, of course, using different terminology. So this terminology of Jordan group was introduced by Vladimir Popov a few years ago. And so Jordan's theorem was probably the first non-trivial statement of this sort. And later, Boothby and Wong extended Jordan's theorem to prove that, in fact, any compact Lie group is Jordan. Boothby and Wong gave a proof which didn't use Jordan's theorem, but you can also obtain their result beginning with Jordan's theorem and then applying the Peter-Weil theorem to. If you have any compact Lie group, by Peter-Weil theorem, you can realize it as a subgroup of some general linear group. And there is a further consequence, which is that, in fact, any finite dimensional Lie group with the only requirement that it has a finite number of connected components is Jordan. And the reason is that any such group has a maximal compact Lie group, which is unique up to conjugation. So if you have any finite subgroup of such a Lie group, then a finite group is in particular compact, so it lies inside a maximal compact group, and by the uniqueness up to conjugation, you can transport any finite subgroup to a fixed compact subgroup, and then you apply the previous statement. Of course, if you remove the hypothesis that the group has a finite number of connected components, then the result need no longer be true. You simply think about a discrete infinite group, for example, the product of all cyclic groups, sorry, not all cyclic groups, product of all symmetric groups, which is manifestly non-Jordan, and look at this as a discrete group, in particular a Lie group of dimension 0. When you study the Jordan property, once you know that a group is Jordan, there is a very natural question, which is to find what is the optimal constant C for which D is C Jordan. And of course here optimal means the smallest possible constant. Now in general, this is going to be a substantially more difficult problem. For the particular case of GLMC, there is the optimal constant is known after the work of Michael Collins, which written here was proved in 2007, and the optimal constant for GLMC turns out to be n plus 1 factorial as soon as n is bigger or equal than 71. The value for the optimal constant for smaller values of n is also known, but it doesn't have any such a nice expression as the general case. The work of Collins is very much related to previous work of Boris Weisweiler, which didn't appear published in its final form. I encourage you to read about the story of Weisweiler. It's a rather sad story, and he made quite important contribution in general in the theory of finite groups, and in particular in questions related to those like Jordan property. Let me finish this slide with a trivial observation. If you have an inclusion of a group H inside a big group D, and you know that D is Jordan, then of course H is Jordan. But of course, the optimal Jordan constant would be smaller for H than for D. Okay, the converse, of course, is not true in general. H could be Jordan while D not being Jordan. Okay, so my concern will be about the Jordan property for typically infinite dimensional groups. And I will devote some time to speak about the case of diffeomorphism groups. So for such groups, Etienne Gis asked around 1990 in several talks whether if you take any closed smooth manifold, its diffeomorphism group is necessarily Jordan. So there has been a lot of activity on this question in the last 10 years. And at present, it is not known precisely in what cases the diffeomorphism group of a closed manifold is Jordan, but there are many cases in which diffeomorphism groups are known to be Jordan. For example, if M is closed and has dimension smaller or equal than 3, then its diffeomorphism group is Jordan. The cases of dimensions 1 and 2 are rather easy to prove. The case of dimension 3 is substantially more difficult and was proved by Zimmermann in 2014 using the geometrization theorem of Perelman. Another case in which the diffeomorphism group is known to be Jordan is that of the so-called rationally hypertorial manifolds. These are manifolds which are closed and connected, and for which you can find a collection of one-dimensional rational cohomology classes whose product is non-zero and lies in the top-dimensional cohomology group. Another instance where diffeomorphism groups are known to be Jordan is for closed manifolds which have the same integral cohomology as a sphere. So these are called integral cohomology spheres. If M is compact, so this means that it could have non-empty boundary and connected, this should be added here, so compact and connected, and its Euler characteristic is different from 0, then its diffeomorphism group is known to be Jordan. And similarly, if M is contractible, its diffeomorphism group is Jordan. At the time when Gis asked his question, there was no known example of a manifold with non-Jordan diffeomorphism group, but these examples turn out to exist. And the first one was found by Chico, Spieber, and Szabo in 2014. They proved that actually, sorry?
And
yes.
Closed and compact, it's the same at the moment?
No, closed means compact without boundary. This is a standard. Yes, this is a standard terminology in manifold theory. Yes.
And in the last item, you don't assume that it's
exactly. Exactly. When I say I'm contractible, I include, for example, the case of Euclidean spaces. Okay, so of course this goes beyond Jesus' question. So then Jesus only asked about closed smooth manifolds. So what Chico, Spieber, and Szabo proved is that the diffeomorphism group of T2 times S2 is not Jordan. And of course, this example is related to other contexts in which one asks about Jordan property, namely for birational transformation groups. And precisely it was known, and this was a theorem of Zarhin, if I'm not mistaken, that the product of an elliptic curve with the projective line has a non-Jordan birational transformation group. And the construction of Chico, Spieber, and Szabo can be extended. In particular, one can prove that whenever you have a smooth manifold supporting an action of an effective action of SU2 or SO3R, the product of T2 with this manifold has non-Jordan diffeomorphism group. So of course, this leads to an infinite collection of examples where the diffeomorphism group is non-Jordan. Okay, so the fact that there exist manifolds with non-Jordan diffeomorphism group is in some sense a very good news, because this means that you can introduce geometry or enrich your geometry and try to find examples in which, despite the diffeomorphism group of M being not Jordan, some subgroups of diff may be Jordan. So let me give some examples of that. You can consider, for example, a Riemannian metric on your manifold and study the isometry group. Okay, so if M is compact, it is immediate that the isometry group of M and Riemannian metric is Jordan. And the reason is that there is a classical theorem by Myers and Steenrod that tells you that these isometry groups are compactly grouped. So you can deduce the fact that they are Jordan from the theorem of Boothby and Wang that I mentioned at the beginning. But if you take a Lorentz metric, then the problem becomes much more interesting, because the isometry group of a Lorentz metric, say on a closed manifold, is certainly a finite dimensional group, but it may have infinitely many connected components. So it's not really automatic that these isometry groups are Jordan. And I proved that if the underlying manifold has dimension smaller or equal than 4, then the isometry group is necessarily Jordan, but nothing is known to my knowledge in higher dimensions. You can also consider complex structures. For example, to begin with, an integral complex structure, and then you can identify this automorphism group with a group of biholomorphisms. And this is known to be Jordan if the real dimension of M is at most 4. And this was proved by Yuri Prokhorov and Konstantin Shramov. The non-trivial case, of course, being that of complex surfaces. But you can relax the condition on J. You can simply ask about automorphism groups of almost complex structures which need not be integrable. And also in that case, if the real dimension of M is at most 4, you can prove that the automorphism group is Jordan. This was proved by myself and my student Carla Saez in 2018. You can also consider a structure of complex projective manifold. So you take on M an integrable complex structure J and a polarization and an ample line bundle. And then the automorphism group is known to be Jordan by a theorem of Meng and Zhang, who actually proved that automorphism groups of projective manifolds, at least over the complex numbers, I'm not sure whether over any algebraically closed field of characteristics 0, they are always Jordan. You can also study symplectic geometry, and if you take a symplectic structure on your manifold M, assuming it supports 1, then you may study the symplectomorphism group, and you can prove that if your manifold has vanishing first Betti number, then any symplectomorphism group is going to be Jordan. This is, of course, not the case of T2 times S2. And you can also study typically a proper subgroup, which is the Hamiltonian diffeomorphism group, which is also defined using a symplectic structure. And in that case, you can prove that it is always Jordan, no matter what the topology of M is. Of course, you need to assume that M is closed.
Sorry,
so,
do you
yes.
assume that M is compact in your here?
In which one? Yeah, I think yes. In everything I am stating, I am assuming that M is compact. Yes.
Okay.
In all these theorems. And there is one example, which is T2 times S2 of manifold, which supports all of these structures. And in fact, for whatever structure you take on M of this type, so Lorentz metric, complex structure, or almost complex structure, of course, projective structure, symplectic structure, you always get Jordan groups. In the case of symplectomorphism groups, this is not a consequence of this general theorem that I'm stating here, but you can prove it using different arguments. And I said that typically the problem of computing the optimal Jordan constant is far more difficult than studying only Jordan property. But for this particular case, if you study symplectomorphism groups, then it is possible to compute the optimal Jordan constant, and it turns out to vary in a rather easy way. Or it depends on an easy way on the homology class represented by the symplectic structure. But this is the only case in which, for this sort of situations, I know how to compute the optimal Jordan constant. We already mentioned that there are other situations which are not subcases of coming from subgroups of the diffeomorphism group, where it is interesting to consider the Jordan property, and of course, I already mentioned the birational transformation groups as an example of that. Okay, so in this talk, I want to go in another direction. Instead of considering subgroups of diffeomorphism groups, I want to consider a bigger group, which always makes sense once you have a smooth manifold, and it makes sense in general for topological manifolds, and which is the homeomorphism group. And to the best of my knowledge, so far, the only theorem stating in a non-trivial case, in a high-dimensional case, a Jordan property for some homeomorphism group is a theorem of Ye from 2017, which states that the homeomorphism group, of closed flat manifolds is Jordan. And the result, one of the results I want to present here is a theorem which in fact proves that basically all cases we knew for the diffeomorphism group, actually you can say that the entire homeomorphism group is Jordan, and even in more situations. So we can say that the homeomorphism group is Jordan in the following cases: for closed topological manifolds of dimension up to 3, for rationally hypertorial topological manifolds, for integral homology or cohomology spheres, and also for topological manifolds with non-zero Euler characteristic. And here, unlike in the older theorem for the diffeomorphism groups, I don't need to assume that the manifold is compact. I only need its integral cohomology to have finite rank and finite torsion, so that the Euler characteristic can be defined. And of course, I need the Euler characteristic to be non-zero. Of course, here you also have the case of contractible manifolds. Let me talk a little bit about the case of integral homology spheres. There is a recent theorem by Zimmermann that states that in any dimension bigger or equal than 5, you can find finite groups acting effectively on Sn, so finite subgroups of the homeomorphism group of Sn, that are not isomorphic to any subgroup of GLN plus 1 R. So this means the following. I mean, you have an action of GLN plus 1 R on Sn. You identify Sn with collection of rays beginning at 0 in Rn plus 1, and the action of the general linear group on Rn plus 1 induces an action on Sn. And this is this action and the restriction of this action to all groups of GLN plus 1 are the so-called linear actions. And what this theorem of Zimmermann tells you is that there are finite groups in any dimension bigger or equal than 5 that act continuously and effectively on Sn, but don't act linearly. It is not known what happens for the diffeomorphism groups. It is, I would guess that everybody believes that such examples also exist for smooth actions, but to the best of my knowledge, so far, nobody has found an example. Such examples would exist only in dimensions bigger than 3 necessarily, and this is a consequence of the following theorems. If you take let me say the following theorem. If you take a sphere of dimension up to 3, then any finite group acting effectively and smoothly on this sphere, for any smooth action is smoothly conjugate to a linear action. In dimension 1, this is an easy exercise. In dimension 2, this is a theorem that was proved independently by Kerek-Yarto and Montgomery-Zippin. And in dimension 3, this is a much more recent theorem, which was proved by Dinkelbach-Lieb using the Ricci flow and the techniques introduced by Perelman. The relevance of such sort of results, especially Zimmermann theorem for our results, is that Zimmermann is telling you that when you state that the homeomorphism group of Sn is Jordan, you are making a statement that affects more groups than the statement that GLM plus 1C is Jordan. Okay, whereas when you state that the diffeomorphism group of Sn is Jordan, it could be the case, but it would be, of course, very, very unlikely. But it could be the case that you are making a statement which affects exactly the same collection of groups as the original Jordan theorem.
Ignasi, I'm a bit confused about what is smooth here and what is just continuous. So you this theorem with many complicated authors.
Yes.
It applies not to homeomorphism of the sphere, right? Only diffeomorphisms. Only
diffeomorphisms, yes. Exactly. And this theorem puts an abstraction to finding example of nonlinear, of smooth actions which are not conjugate to linear actions in dimensions 1, 2, and 3. Okay. We don't know anything about homeomorphism groups of S4, for example. Okay. So whereas Zimmermann theorem, the groups that Zimmermann constructs act continuously, and the action is not smooth. I don't know if this clarifies your question.
Okay. And so and then another question.
Yes.
So the group which exists in the just to understand the gap between theorem with many authors and Zimmermann's theorem.
Yes.
So Zimmermann has an example for homeomorphisms of high-dimensional spheres.
Yes.
With many people claim that everything is nice for diffeomorphisms of low-dimensional spheres.
Yes.
And there's no assertion for homeomorphisms of low-dimensional spheres, and there is also no examples for diffeomorphisms of high-dimensional spheres, right?
Yes. Yes, I mean, you can say, for example, what is known is that if you consider homeomorphisms of S3, for example, not all finite groups, not all continuous actions of finite groups on S3 are continuously conjugate to linear actions. There are examples of pathological actions. So there is a very famous construction by Bing, I think it's from the 60s, of an involution of the three-dimensional sphere whose fixed point set is not even locally linear. So, and this of course prevents it from being conjugate to a linear action. Okay. Okay. So let me say a few words about how one proves that theorem. For the case of closed manifolds of dimension up to 3, one can proceed as follows. The first step consists on noticing that M admits a unique smooth structure. This is a classical theorem. In dimension 2, it was proved by Radot, and in dimension 3 by Moitz. And then there is another statement, which is that every finite subgroup of the homeomorphism group of M is isomorphic to a subgroup of the diffeomorphism group. In dimension 2, you can make a stronger statement, because you can prove that any finite subgroup of homeomorphism group of M is conjugate to a smooth, to a subgroup of the diffeomorphism group. And this is what actually Radot proved. In dimension 3, this is not true because of the example of Bing that I mentioned. But nevertheless, John Pardon managed to prove 1 year ago that still, and I mean precisely that statement that is written here, that any finite subgroup of homeomorphism group is isomorphic to a subgroup of the diffeomorphism. And now you can finish the argument by using Zimmermann's theorem that states that the diffeomorphism group of such M is Jordan. Okay? And the conclusion is that the homeomorphism group is also Jordan. How about rationally hypertorial manifolds? Suppose that M is such a manifold, denoted by pi its fundamental group. And now the hypothesis that M is rationally hypertorial can be translated in geometric terms by stating that there is a map of non-zero degree from M to a torus of the same dimension of M as M. Now let lambda denote the kernel of the induced map of at the level of fundamental groups. I'm being a little bit sloppy here with base points. Of course, one needs to be a bit careful with that. And now any action of a group, any continuous action of a group G on M induces a morphism from G to the outer automorphism group of pi. Of course, if the action preserves the base point, then this is an action by automorphisms. But in general, you cannot expect the base point to be fixed. So you only have an action at the level of automorphism, of outer automorphism. Outer automorphisms. And now there is a theorem by Gottlieb, Lee, and Usaydin from '85 that says that if G is compact and you assume that the action by pi by outer automorphism preserves lambda, the kernel of the morphism to Zn, the fundamental group of Tn, and the induced action on the quotient of pi by lambda is trivial, then such G is necessarily abelian. So then you can invoke a famous lemma of Minkowski, which I'm going to state later. Let me say it now. It says that if you fix n, then there is a uniform upper bound on the size of the finite subgroup of GLNZ. And this implies that if G is finite, then there is a subgroup of G of bounded index, which satisfies the hypothesis of the theorem of Gottlieb, Lee, and Usaydin, and hence is abelian. So this proves that the homeomorphism group of such M is Jordan. Let me now talk about the case of manifolds, both homology spheres and manifolds with non-zero Euler characteristic. And here the main ingredient is a recent theorem by Chico, Spieber, and Szabo that states that to study the Jordan property for homeomorphism group, it suffices to consider the finite P subgroups of the homeomorphism group for all choices of prime P. Okay, so more precisely, if you prove that there is a constant C such that for any prime P and any finite P subgroup G of the homeomorphism group, there is an abelian subgroup A of G whose index in G is at most C, then automatically the homeomorphism group is Jordan. Of course, the Jordan constant need not be the same one as C, and the arguments always give much bigger constants. Just to give you an idea of the importance and of such result, let me mention what ingredient I used to prove the Jordan property for some diffeomorphism groups. And this is a theorem by myself and Alexandra Turull, which gives a general criterion for the Jordan property. It states the following. It says that it suffices to consider only finite subgroups of your group whose cardinal is the product of at most 2 prime powers. So this is much more general than P groups, as in the case of the theorem of Pico, Spieber, and Szabo. And you only need to consider the case in which for one of the 2 primes you have a normal zero subgroup. Okay, and then the consequence is that the group D is Jordan. In fact, you can prove that if you want to have a general theorem for arbitrary groups, then you cannot improve this. there are groups for which, if you only consider P subgroups, they look as if the group was Jordan, but the group is actually not Jordan. So you need to do some geometry to pass from such a statement to a statement telling you that P groups suffice. In the case of smooth actions, there is an argument which uses the linearization of the action along fixed points on the normal bundle, okay? But in the topological setting, you don't have normal bundles, you don't have tangent bundles, so the passing from this theorem about finite groups with two prime divisors to the theorem of Chico, Spielberg, and Szabo mentioning only P groups, it is a really challenging problem, okay, which Chico, Spielberg, and Szabo managed to solve. Okay, so now, for example, let's talk about the case of manifolds with non-zero Euler characteristic. And we know that it suffices to study P groups. So suppose that you have a finite P group with P an arbitrary prime number, okay? And we assume that G acts continuously on topological manifold and satisfying, I mean, you assume your manifold to have finite dimensional homology over Z mod P. Now define Mi to be the set of points in M whose isotropy group has cardinal P to the I. Now there is a theorem by Ye which says the following. Assume that the cardinal of G is P to the N, then the dimension of the homology of Mi with coefficient in Z mod P is finite for all I. This allows to define the Euler characteristic of these pieces, and the Euler characteristic of M turns out to be the sum of the Euler characteristics of each of the Mi. Furthermore, the Euler characteristic of Mi is divisible by P to the N minus I. Okay. Well, this has an immediate corollary, which is that if P to the R is the highest power of P, which divides the Euler characteristic of M, then necessarily there exists some point in M whose isotropy group has index in G at most P to the R. Okay? And now the next step is going to be to study such a group. Of course, if we prove that for one such isotropy group there is an abelian subgroup with bounded index, then we have finished. Let me mention, of course, that our initial assumption that both the rank and the torsion of the integral homology of M are finite implies that the homology with coefficients in Z mod P is finite for all primes P. Okay, that is by the universal coefficients theorem. And then, of course, the Euler characteristics coincide. Okay, so what can we do once we know, once we have an isotropy group? In the smooth setting, the situation is very favorable once you are in that setting, because if you have a finite group acting smoothly and effectively on an n-dimensional smooth manifold, then the isotropy group of every point is isomorphic to a subgroup of GLNR. And of course, then you can apply in that setting Jordan's theorem for GLNR and conclude that isotropy groups have abelian subgroups of bounded index. This lemma is probably very well known, but let me briefly recall the proof. You need to choose a invariant Riemannian metric on your manifold, and the way to do that is to take first any Riemannian metric and then take your metric to be the average over the action of G of the translates of this initial Riemannian metric. Once you have a G invariant and a G invariant Riemannian metric, and you take any point X, then the exponential map is a local diffeomorphism, which is equivariant, is G equivariant in the sense that it intertwines the linear action of G on the tangent bundle and the original action on of G on M. And now this implies that the linear action of Gx on the tangent bundle is effective. And of course, you identify the linear automorphism group of that can be bundled with GLNR, and you obtain the lemma. The question is whether such lemma is true in the topological category. Suppose that instead of acting smoothly, your group G acts continuously and effectively on a topological manifold. Unfortunately, the answer is that the lemma is not true. In fact, you can find examples justifying this using the construction of Zimmermann. Just take G to be any of these examples of finite groups that act continuously and effectively on Sn, but are not isomorphic to subgroups of GLN plus 1R. Okay? And then you take the cone of Sn, and then there is an induced action of G on the cone that fixes the vertex, but of course the cone of Sn and vertex is homeomorphic to the pair Rn plus 1, 0. So you get a finite group that acts continuously on Rn plus 1, fixing the origin, and nevertheless, this group is not isomorphic to any subgroup of GLN plus 1. So this justifies that the previous lemma is not true in the continuous category. However, the good news is that, yes?
Fails in the continuous category starting from dimension 6?
Yeah, of course, yes. This argument only proves that the lemma is not true in dimension 6 and bigger. I don't know about smaller dimensions. In very small dimensions, the lemma is probably true, but I have no idea about dimensions 4 and 5, for example. Okay, so there is good news, and the good news is that if instead of considering arbitrary finite groups, you consider only finite P groups, then the lemma turns out to be true. And this is based on a theorem of Dotzel and Hambrick, which I'm now going to recall. Suppose that P is a prime and G is a finite P group. And suppose that you are given a function that assigns a non-negative integer to every subgroup of G. Let's call nu to this function. You require this function to satisfy the following conditions, which are really called Borel-Smith conditions. So the first condition is that if you have two subgroups, K and K prime of G, and K being a normal subgroup, and you also assume that the quotient of K prime by K is isomorphic to Z mod P to the square, then you want to have the difference between nu of K and nu of K prime to be equal to the sum over all groups H lying between K and K prime, so that the quotient by H is isomorphic, so that the quotient by K is isomorphic to Z mod pi, Z mod P, of these contributions here. There are other conditions. Of course, you want the function nu to be growing. So I think this is a mistake. I think this should be the other. No. That's sorry. This is okay. It is a decreasing function in general. So if K is a subgroup of K prime, you want nu of K prime to be at most nu of K. And you also require that if P is odd, that difference has to be even. And you also want the function to be invariant under conjugation. And for the prime 2, you also want this extra condition. If you have now 3 subgroups, K, K prime, and K double prime, and you assume that K prime and K prime mod K is isomorphic to Z2, and K double prime divided by K is either general quaternion or isomorphic to Z mod 4, then you want these extra divisibility conditions. I'm not going to use them. Let me ignore the detail of these conditions. The important thing is that once these conditions are satisfied, there is a theorem that tells you the following. If nu of K is strictly smaller than nu of 1, the trivial subgroup of G, and you call n this nu of 1, then G is isomorphic to a subgroup of GLNR. Okay, so this is a numerical criterion to check that a given finite P group lies inside GLNR. As we will see, the theorem of Dotzel and Hamrick works very well in the context of continuous actions.
This function always exists?
Excuse me?
Does this function nu always exist?
Sorry, I don't understand. Say it again.
I asking that does this function nu always exists, or it is like existence of this function?
The existence of this function. So what?
The existence of this kind of function nu is always exists this function for any group.
Well, I mean, if you have any, okay, you're asking whether the converse is true. I mean, if you have a finite P group, then
I'm saying that whether this function always exists or not.
Well, maybe
you always have such functions. That's true. If G is an infinite P group, you can always find such functions. So you only need to embed G inside a linear group, which you can always if G is finite. Okay.
Yeah.
And now you define nu of K to be the dimension of the subspace, the linear subspace fixed, or the space of vectors fixed by G. Okay.
Okay. So for finite P groups, it always exists.
They always exist. Yes. Yes.
Okay.
Yeah. I mean, what the non-trivial part, when you want to apply this theorem, the non-trivial part is to find a function nu such that nu of 1 is small. Okay?
Yeah.
Okay. So for topological actions, this works very well. So suppose that G is a finite P group acting continuously in a topological manifold. Suppose that X is a point fixed by G. Then for every subgroup H of G, the fixed point set of H is a Z mod P homology manifold. So this is an old theorem of Smith. The meaning of a Z mod P homology manifold roughly is the following one. It is a manifold whose local homology looks like the local homology of a topological manifold when you take coefficients in Z mod P. Okay, the actual definition is a bit more involved. You have to define a sheaf beginning with the presheaf of the Borel-Moore homology with coefficients in Z mod P. You sheafify this presheaf, and you want the resulting sheaf to be a local system. Okay, and every homology Z mod P homology manifold has a dimension which is defined locally, and then you define nu of H to be the dimension of this fixed point set at the point X. And this is going to be a non-negative integer. And then you can prove that such function satisfies the Borel-Smith conditions. So in particular, you get an embedding, which is an abstract embedding of G inside the general linear group of the same dimension as your manifold M of X. The proof combines classical results on equivariant homology by Borel, Bredel, and Tondik.
And is it
Yes?
does it come together with some geometric identification? So before, now you already have an embedding to some GL of some vector space.
Yes.
Does it have some common features with something which can be interpreted as a tangent space?
Yeah.
Version of this theorem.
Well, let me see. Actually, the actual result of let me go back to the theorem of Dotzel and Hamrick. The actual paper of Dotzel and Hamrick proves something of this sort. So what I have written here as a theorem is in fact a lemma in the paper, but it's half of the paper is that lemma, and the construction is It doesn't use any geometry, that construction, but what Dotzel and Hambrick afterwards prove is a theorem which identifies, which characterizes integral homology spheres as those supporting actions of finite P groups with this type of functions, nu. Okay, but Dotzel and Hambrick work in the category of CW complexes. Okay, so they don't work with tangent spaces, but nevertheless there is an inductive procedure in their construction which you can vaguely relate to tangent spaces. I mean, there is a, so, or say in different words, there is some geometry behind this construction of the embedding inside GLNR. And now there is a corollary, which is that if a finite P group acts continuously and effectively on Sn, then it is isomorphic to a subgroup of GLN plus 1. Okay, you can prove this by using the cone construction. You take the cone of Sn, and then you identify this with Rn plus 1, and you apply the previous theorem. But you can, of course, alternatively prove the corollary using classical theorems of Smith and Borel and Breton, and check. So these classical theorems tell you that the fixed point set of a finite P group action on a sphere is going to be a homology sphere with a homology Z mod P, sorry, a Z mod P homology sphere, and then you have a control on the dimension. And so there is a collection of theorems which are parallel. There are two collections of theorems, sorry, theorems for local homology and theorems for homology of actions on the sphere. You can use both to prove this corollary. And using that corollary, combined with the theorem of Chico, Spieber, and Szabo, you prove that the homeomorphism group of spheres homeomorphism groups of spheres are Jordan. And you can also, of course, sorry, let me go back here. And using the theorem, you also prove, combining the theorem with Chico, Spieber, and Szabo and the fixed point theorem of Yi, you prove that the homeomorphism group of topological manifolds with non-zero Euler characteristic is Jordan. Now, I would like to explain two applications of this of this theorem. The first one is an easy consequence, but it's interesting in view of the examples of Zimmermann. It tells you that if you are given some number n, you can find another number, let's say big N, and that any finite group acting continuously and effectively on Sn is isomorphic to a subgroup of GL big N R. Okay, and this is interesting because precisely Zimmermann tells you that this big N cannot be the same as small n as soon as small n is bigger or equal than 5. And the proof is quite easy. You use Jordan's property for the homeomorphism group of the sphere, and then a classical theorem of Mansoux, which implies that if you fix the dimension of the sphere, there is some n0 such that any abelian group acting, any finite abelian group continuously and effectively on the sphere embeds inside GLN0R. Okay? And then you use the induced representation. There is and
so you don't use the previous theorem about P groups at all?
Oh yes, as an ingredient, yes, because here you use the Jordan property, and to prove the Jordan property, you use that theorem for P groups.
I see.
Yeah. Yeah, I mean, for P groups, big N is equal to small n.
I got it. Yeah. So I just didn't notice that you already finished the proof of Jordan for
yes. Okay, second application. Suppose that M is a compact topological manifold with non-zero Euler characteristic. Then there is a number C such that for any action, any continuous action of finite group G on M, you can find a point in M whose stabilizer, whose isotropy group, has index at most C. And this property I call the almost fixed point property. Okay, So I gave a talk in the Steklov Institute 2 years ago about almost fixed point properties for smooth actions. And the theorem also required a stronger property than the non-vanishing of the Euler characteristic. So I needed to use that the manifold has no odd homology, so that all the integral homology is supported in even degrees. So this theorem extends that theorem in these two directions. It includes the possibility of mainly merely continuous actions, and also it applies to a much bigger collection of manifolds. Let me say a few words about this almost fixed point property. Let me mention three theorems. First theorem by Buchdahl, Kwasik, and Schutz states that in dimensions up to 4, any smooth finite group action on Dn has a fixed point.
So Dn is a disk, right?
Sorry?
Dn is a disk.
Even the closed disk, yes. Yes. However, in dimensions bigger or equal than 6, there do exist finite group actions without fixed points. And this is also proved in the same paper by Buchdahl, Kwasik, and Schutz. And however, by the theorem that I wrote in the previous slide, Dn has the almost fixed point property. So although there are actions without fixed points, there is a bound on how far any finite group action is from having fixed points, because there are points whose stabilizer is mainly not, maybe not the entire group, but it's very close to it.
Just in case, so
yes.
In dimensions 1 and 2, you don't require smoothness.
No, this is, yeah. For dimensions 1 and 2, you can prove the same thing for continuous actions.
For any action, right?
Yes.
And where do things break down?
I don't know about dimension 3. As far as I know, all non-results refer to smooth actions.
I see.
But I'm not 100% sure. And let me give a third example. And this example proves that the hypothesis that M is compact is crucial in that theorem. Because there are, in Euclidean spaces, in any dimension beginning with 7, for any number C, you can find a continuous action of a finite group on Rn, all of whose stabilizers have index inside G bigger than C. Okay. Now let me mention the ingredients of the proof of the theorem. There are three ingredients. One is the Jordan property. So the Jordan property is going to allow us to restrict to actions of finite abelian groups, because we know that passing to abelian two groups can be done with a controlled index. Now I will need a notion called lambda stability and a bound on number of stabilizers. I'm going to talk about these two properties, lambda stability and bound on number of stabilizers, in the next slide. Right. Let's talk about lambda stability. Let lambda be a number, and suppose that a finite group G acts continuously on M. Then we say that the action of G on M is lambda stable if all isotropy groups that are different from the entire group G have index bigger than lambda. Or put it in other words, whenever you have a point whose stabilizer has index smaller or equal than lambda, then this stabilizer is automatically the entire G. Okay. Now there is a theorem which tells you the following. In general, if you're given a manifold M and you choose some lambda, then of course there is no reason to expect that any action of a finite group G on M is going to be lambda stable, of course. But the theorem tells you that you can pass to a subgroup of controlled index and then have the restricted action is going to be lambda stable. So this is the precise statement. You fix a topological manifold, compact topological manifold M, and a number lambda. Now there is a number C, which is going to depend only on M and lambda, such that for every prime P, every finite P group G, and every continuous action of G on M there is a subgroup G prime of G with index at most C in G, and the action of G prime M is lambda stable. The idea of the proof is a sort of descending chain condition for isotropy groups in a uniform sense. Concretely, there is a constant C prime such that if you have a decreasing sequence of subgroups beginning with G, G0, G1 up to GR, and the fixed point submanifolds of these subgroups are strictly increasing, then this chain cannot be arbitrarily long. And the proof of this descending chain condition is elementary using classical results of Smith. Namely, you can control the sum of the Betti numbers with coefficient in Z mod P of all of these fixed point submanifolds. In particular, you control the number of connected components, and then an elementary argument leads you to this bound C prime. Okay, now let me talk about this bound number of stabilizers. So this is a theorem by Chico, Spieber, Sabo, and myself, which says the following. Suppose that M is a compact topological manifold, then in general, your manifold is going to support actions of big groups. Of course, not for every manifold, but there are manifolds where the size of the finite groups that may act effectively there is unlimited. Nevertheless, there is some limit on the number of different isotropy groups that you encounter. Okay, there are two different statements. Given the statement is that there is a constant, in both statements, sorry, claim that there is a constant C, such that for any prime P, any finite P group G, and any continuous effective action of G on M, if you consider the collection of all isotropy groups, then up to conjugation, they are bounded, the number of them is bounded by C. Okay, so sorry, I'm saying the second statement. And the first statement says that if you pass to a subgroup of index at most C, then the collection of all isotropy groups, no need to mod out by conjugation, contains at most C elements. Okay, a general statement about number of isotropy groups without conjugation and holding for G cannot be true. You simply think of the action of dihedral groups on the circle. Okay, there you have as many isotropy groups as vertices in a regular polygon. Okay, of course, all these isotropy groups are conjugate. A few words about the proof. The general case is deduced from the case of abelian group, and in fact, for the theorem about the almost fixed point property, this is the case that this is the only case that you need, case of abelian G, and the case of abelian G is reduced to the case of elementary abelian, so Z mod VR, and this is proved by induction on R. So Manch's theorem tells you that this R cannot be arbitrarily big, and then you use ascending induction on R. Okay? You control the size, the number of isotropy groups in terms of the size of the equivariant homology. It is a bit tricky because all isotropy groups contribute in different ways, but using induction, you can manage to find such bound. Okay, if you look at the second statement of the theorem, of course, when G is abelian, conjugation is trivial. So what you get is that the number of isotropy groups is bounded by C. Now let me, I'm going to finish with 2 more slices. Let me sketch the proof of the almost fixed property using the previous results. So first, a statement about P groups. Suppose that M is a compact topological manifold, P is a prime, and you have an abelian finite P group, G, that acts continuously and effectively on M, and suppose that the action is trivial on homology. Then by the theorem I explained about lambda stable actions, if you take C to be the constant in the previous theorem means the one about number of isotropy groups, then you can assume that the action is C stable up to passing to a subgroup G prime of G of bounded index. Now, consider the union of the unions S of all isotropy groups of the action of G prime, which are not G prime itself. Okay. Now, we know two things about G prime, about the action of G prime on M. We know that the action is C stable. So any isotropy group which is not the entire group will have index at most C. So it's the number of its cardinal is going to be at most the cardinal of G divided by C. On the other hand, we know that there are at most C different isotropy groups. So we have at most C groups, sorry, at most C subgroups. Each of them has at most the cardinal of G prime divided by C elements. Of course, all of them have the identity element in common. So the union, namely S, cannot be G1. Okay? Well, let's take some element, little g, in G prime not contained in S. And what can we say? Well, we know that the action of this element, little g, is non-trivial because little g acts trivial on homology, and the Euler characteristic is different from 0. So the Lefschetz fixed point theorem tells you that there are fixed points. Okay, but the interesting thing is that these points which are fixed by the element little g are in fact fixed by the entire group G prime. Because just take any point fixed by little g. Well, it's going to have some isotropy group, but this isotropy group is going to contain little g. But little g doesn't belong to S. And S is the union of all isotropy groups which are different from G prime. And consequently, the isotropy group of such point has to be G prime. So that point has to be fixed not only by G, but by G prime, the entire group G prime. So this is the argument for actions of finite abelian P groups. Now, what can you do in general? Well, in general, you can, if you have any finite abelian group, you can represent it as the product of its P parts. But first, let me state the lemma of Minkowski that I have already mentioned at the beginning of the talk. It says that there is an upper bound on the size of the finite subgroups of GL and Z that only depends on N. Okay? We don't care what the bound is. Now suppose that A is a finite abelian group that acts continuously and effectively on M. This A is going to come from applying the Jordan property to the action of an arbitrary finite group G that acts continuously and effectively on M. Okay, so we apply Jordan property, we get A. Now, by Minkowski lemma, there is a subgroup B of A that has bounded index and that acts trivially at the level of homology. Now, let BP be the P part of B. Okay, so these are the elements of order P. Now, there is, by the previous slide, there is an element gamma P in BP and an element and a subgroup BP prime with index at most C that is a constant depending only on M, such that gamma P has non-trivial fixed points, and all points fixed by gamma P are fixed by the entire group BP prime. Now, take the product of all gamma P's. Of course, there's going to be a finite number of primes P for which this gamma P is different from the identity, namely the primes that divide the cardinal of B. And let B prime be the product of the BP primes. Well then, MB prime, the points fixed by B prime are going to be the points fixed by BP prime for all primes P. However, this is equal to the points fixed by gamma. and this is by the Chinese remainder theorem. Okay, so we define gamma this way, but of course, for any prime p, we can get a power of gamma that is equal to gamma p. Okay, and then this justifies this equality, second equality here. And now this is different from the this is non-empty because of Lefschetz fixed point theorem. Now let Q be the amount of primes not bigger than C. Remark that if you take a prime that is bigger than C, then BP prime is equal to BP. And so if you want to compare B with B prime, for primes bigger than C, they will be the same ones. Only for primes smaller than C, you will get a possible discrepancy, but that discrepancy is going to be by C. So if Q is a number of primes not bigger than C, then the index of B prime inside B is at most C to the Q. And remembering that C depends only on M, we get a constant that only depends on M. And what we have proved is that there is such a subgroup B prime which has bounded index and which has fixed points of the action on M. And this finishes the proof of the theorem on the almost fixed point property, and this finishes my talk. So thank you very much.
Thank you. Like plenty of interesting assertions. Most of them, I suspect, very unfamiliar to most of our participants. So, are there any questions? I have just a couple of very small questions. Did I get it right that so at the very beginning you commented on the you briefly sketched the proof of the hypertoral
yes,
right?
Yes.
Case, and did I get it right that first you proved it for diffeomorphisms, but
yes,
the proof actually is the same in the for continuous actions?
No. My argument for smooth actions is different from the theorem of Gottlieb, and let me go back to that. Yeah, so my argument is different from the argument of Gottlieb, Lee, and Uzaidin. The theorem is actually weak. My theorem is actually weaker and proved a few years afterwards. But the paper has the interest that the argument is different.
Mm-hmm. Okay. And then maybe so and then maybe just on the next slide from this, you
Yes.
You told about this Chicos-Kleber-Żaba theorem.
Yes.
And can you give some like brief, maybe not explanation, but maybe not the idea of the proof, but what's the idea why it should ever be true, something like this. So what? Well, okay, I understand that.
Yeah.
In the later slides, you showed that for P groups you have some additional for P group continuous action of P groups you have plenty of additional information,
yes,
like with embeddings and whatever. But is there a very brief or rough idea why this reduction to P groups should be true while it's not true in the arbitrary group theoretic case?
Yeah. Well, there is some geometry behind the statement. I can give you the argument for smooth actions and explain you how things go for continuous actions. For smooth actions, one possibility is to deduce that theorem from this other theorem with Alexandra Turull, although Chicos-Kleber and Szaba use a different input from group theory. So they have a different argument, and then they obtain a very powerful theorem. But you can also use this theorem, which gives you a general criterion for arbitrary groups. And now what you need to prove to pass from groups with two prime divisors to groups with one prime divisors, namely to P groups, what you need is to assume that you have a group G whose of this sort here in the theorem with Alexander's rule, and you want to prove that it contains, so you assume that this group acts smoothly, let's say smoothly first, on your manifold, and you want to prove that it contains a big, that you want to assume that if for P groups you have Jordan property, then for these groups you also have Jordan property, okay? And at the end, you end up having to study groups which are extensions of an abelian P group by a cyclic Q group with Q a constant, a different prime, okay? And now you can understand this using some, using the spectral sequence for the Q-variant homology for the group action of Z mod P to the N. And this spectral sequence has an action of Q, of Z mod Q everywhere, okay? And you consider the weights of this action on the terms of the spectral sequence. If the action of your group is free, then looking at the weights, you end the proof. I mean, you conclude that either Q is very small or the action of Z mod Q on Z mod P to the N is trivial, or yeah, exactly. But this works only for free actions. Now, to pass from the general case to the case of free actions, in the smooth category, there is a trick, which is to pass to the frame bundle. I think I explained this in Yaroslav. Yeah. Okay, you take an invariant Riemannian metric and you take the orthogonal frame bundle. And then the induced action there is free. Now this works in the smooth category, and in the topological category, it's much more tricky. You need to you also work with the spectral sequence for the equivariant homology, but you need to rely on results about homology manifolds and homology of the complementary. I mean, the flavor is similar, but the techniques are different.
I see. Maybe as a side comment, it's a very common situation. There's a like many of Jordan type results have their parallels in the context of group of birational self-maps.
Yes.
As we know, some of the birational results used to precede the corresponding smooth manifold results, like this counterexample by Yuri Zarhin and by Chikos Piberzhaba. But it seems that there is still no analog of this theorem, reduction to P groups in the birational world. At least,
yeah.
Which I would know.
Yeah, this would be very interesting. And in fact, another thing which maybe would be interesting to explore is to find applications of the theorem of Dotzel and Hambrick in birational geometry. Okay.
Can you remind us again, Dotzel and Hambrick?
Yes, this theorem by this slide here. Okay. So this theorem was obtained having with the motivation of continuous actions. L'ultimo moment, sisplau, que encara no he acabat. Sorry. 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 Okay. So this theorem was devised for continuous actions, and of course the typical example of the function nu is the dimension of the fixed point submanifolds. Okay, so this is what I use this definition here. Okay, but who knows? Maybe in birational geometry, assuming that you have a finite P group of birational transformations, maybe in some context there is a possibility of defining a function nu satisfying this Borel-Smith condition. I don't know. I mean, it's very speculative.
Well, at least leaving aside these complicated conditions, at least I have also never seen any construction which is on the next slide, like just this stratification by fixed points of subgroups. I think it was also never used in the algebraic context.
Yeah. I don't know. I mean, I don't know in the birational case, for example. Of course, if you say birational transformations, then I guess you don't care so much in first instance about fixed points because you can remove them and you get something birational equivalent. But if you look for compact models, proper models of your manifold on action, then maybe fixed points can play a role.
Yeah. Okay. Any further questions? If no, then thank you, Ignasi. It was very amazing. And